Hello, welcome to the second of our talks in the ThUNDDAR series on therapeutic ultrasound. My name's Eleanor and I'm going to be talking about bubble basics, or the role of cavitation in therapeutic ultrasound. So just to start off with some definitions, the dictionary definition of cavitation is the formation of bubbles or cavities in a fluid. The second line talks about the motion of propellers, which gives you an idea of the historical context in which cavitation was studied. But in therapeutic ultrasound, we just go with the first part. So it's the formation of bubbles or cavities, and then particularly the response of those bubbles or cavities to the ultrasound field. I would sound a note of caution here. Definitions vary between different fields, so depending on who you're talking to, it's important to make sure you're clear about what you mean by cavitation. Now, what actually is a bubble or a cavity? It's a space of one medium within another. Now, theoretically, that space could contain absolutely nothing. It could just be a vacuum. In reality, though, it's going to contain either a vapor, i.e. some of the surrounding medium material in gaseous form, or a gas, i.e. another medium also in gaseous form within that space. And most typically, we're talking about bubbles that contain both. So we have a region, usually in a liquid, containing a mixture of gas and vapor. Now, there are lots of examples where cavitation occur. I briefly mentioned propellers in the dictionary definition, where you have machinery rotating very, very quickly in a liquid. The pressure drop associated with that motion can be sufficient to produce bubbles. Everyone is obviously familiar with boiling, whereby the temperature in the liquid is sufficient to create a phase change and you get boiling bubbles formed. A slightly more gruesome example is so-called ballistic cavitation, where you have one object moving very, very rapidly through another material. And again, there's a pressure drop associated with that motion that can create bubbles. So this is a bullet wound that's been created as a result of cavitation from a bullet passing through tissue. And then, of course, one we're definitely all familiar with, which is where you open a bottle of fizzy drink a little bit too quickly, and the very, very rapid pressure drop associated with that creates a lot of bubbles very, very quickly. So pressure and temperature are both very, very important for cavitation, and there are several reasons for that. First is that both of these control the state of a material. So whether it's a solid or a liquid or a gas, what you're looking at here is the phase diagram for water. So depending on where we are in terms of pressure or in terms of temperature, the medium will exist in one of these three different phases. So as we move up in temperature, we're more likely to have a gas forming, and similarly as we move up in pressure, we're more likely to have a solid. In addition to that, both the pressure and the temperature determine how much gas can be dissolved in a liquid. So the cooler the liquid, or the higher the pressure it's under, the more gas can be dissolved in that. And that can be calculated using Henry's law. So the partial pressure of a particular gas depends on the Henry's constant for the gas and the surrounding liquid, and that gives you the dissolved concentration. And the last thing, both pressure and temperature also determine the size of any pre-existing bubbles in the medium. So I'm sure you're all familiar with the ideal gas law, but as we increase the pressure, bubbles will get smaller, or as we increase the temperature, bubbles will get larger. For now, we're ignoring any gas going in and out of the bubble, but pressure and temperature control the size of pre-existing bubbles. So what we haven't looked at, though, is what happens when bubbles start to move. At the moment, we're just talking about the static pressure and temperature in a liquid, and that determines whether it is thermodynamically favourable for a bubble to exist. It doesn't mean that a bubble will exist. Because when we create a bubble, we're creating a new surface, and there's energy associated with that surface that also needs to be provided for the bubble to exist. Now, if we're just talking about pure water, then the energy we need to provide needs to be sufficient to overcome the hydrogen bonds in water, i.e. to stretch it apart to create a cavity. So we need to overcome the tensile strength in water. Turns out, however, that tensile strength is extremely large. It's 10 to the 8 pascals, which is 1,000 times atmospheric pressure. And needless to say, we're not normally imposing those sorts of pressures on a liquid in therapeutic ultrasound or in any other situation. So just as you know from opening a bottle of fizzy drink or from popping a bottle of champagne, we can create bubbles clearly at much, much lower pressures and without having to raise the temperature. So there's another factor we need to consider that can determine whether bubbles can form. And that is the fact that typically something exists, there's an impurity already existing in the liquid that allows bubbles to form at much, much lower pressures or without providing these huge amounts of energy. Now, we don't fully understand what these are, but the hypothesis that's now widely accepted is that there are already discontinuities within the liquid, so places where the medium structure is disrupted, that act as so-called bubble nucleation sites. So places where the surface energy is already higher, that energy has already been provided, so we need a little bit more for a bubble to be created. Exactly what these sites are, not entirely established, but they're believed to either be pre-existing bubbles, so sort of a few tens, hundreds of nanometers, stabilized by a surfactant adsorbed onto the surface, or little crevices or pores, either in the surface of the container for the liquid or free-floating particles within that liquid, where again, gas can be stabilized in these little crevices, providing a nucleus for a bubble. And crucially, the pressure inside these nuclei is lower than the external pressure, so the gas is stabilized. What happens when ultrasound is passed through a medium is that the pressure and the temperature will both vary locally as the medium is expanded and compressed. And that additional energy being provided by the ultrasound wave is enough to nucleate the bubble. Now, as Robin talked about last week, depending on the type of tissue that the ultrasound is passing through, the amount of energy that gets absorbed will vary. So different types of tissue have different attenuation coefficients, and also the frequency of the ultrasound will depend how much energy is getting deposited, and also how rapidly the tissue is being expanded and contracted. So if we have a medium and it contains these nucleation sites, different things will happen depending on how much energy we're able to sort of propagate into that medium as the ultrasound passes through. So the characteristics of the medium are important, pressure and the temperature is varying, so the physical properties of that medium and the dissolved gas concentration are important. Then of course the nuclei themselves, their size, the quantity of them, the surface tension on them, that's going to determine how easy it is for the bubble to form and how much gas they contain. And then of course the sound fields, so frequency, the amplitude, the duration of exposure, and then how frequently we're sending pulses and the length of those pulses. So all of these together are going to determine whether or not a bubble can form from the nuclei. And we can sort of think of this in terms of a flowchart. So first of all, does the ultrasound provide a sufficient pressure drop for bubbles to form? If not, then is sufficient temperature, is sufficient energy being deposited for there to be a temperature rise? If not, then there won't be any bubbles formed. If the pressure drop is not sufficient, but we do get enough heating, then we'll tend to get large bubbles containing both gas and vapor forming, i.e. we'll get boiling. If, on the other hand, the amplitude of the ultrasound is sufficient that when the pressure drops, bubbles are able to evolve from the nuclei, then we will get acoustic cavitation. And of course, we may have a combination of both a sufficient pressure drop and a sufficient temperature rise for bubbles to form, and we'll get a combination of boiling and acoustic cavitation. Now, how can we calculate how much pressure is required? Well, the minimum pressure that we need is enough to basically overcome surface tension, so to enable the bubble to grow against the surface tension that's holding it together. And we can calculate that by thinking about the gas pressure inside the bubble and also the vapor pressure, so the combination of those competing with the hydrostatic pressure in the surrounding liquid and the surface tension at the interface. And if we rearrange that pressure balance, we can get an equation telling us what the minimum pressure is we need to enable the bubble to expand. And that's known as the Blake pressure. Or if you want to look at another way, for a given applied pressure, critical bubble size for it to be able to grow is known as the Blake radius. That, on the other hand, is only looking at a quasi-static situation where we're applying a pressure and holding it, and the bubble has enough time to expand. When we're talking about an ultrasound field, clearly the pressure is varying with time, and so we need to also think about the dynamic response of the bubble as well. Once the bubble starts to grow, not only is it having to grow against surface tension, but it's also having to push the surrounding medium out the way. So the inertia of the surrounding liquid will resist the bubble's expansion, which would obviously depend on how fast the bubble is accelerating and also the square of the velocity. And then clearly there's going to be some energy loss, so the viscosity of the liquid will also draw energy out of that process and resist the bubble's motion. So we have surface tension, we have liquid inertia, and we have viscosity. And if we then apply Newton's second law and we come up with an equation that describes the dynamics of a bubble, we end up with this rather horrible looking nonlinear equation known as the Rayleigh-Placid equation, which describes how a bubble will actually respond to an ultrasound field. So we have the density of the surrounding liquid and the acceleration of the bubble wall. So basically this is the MA term in F equals MA. It's nonlinear, as you can see from the R squared term. And then the combination of forces on the right hand side is the vapor pressure and the hydrostatic pressure. So the inside the bubble and outside the bubble, the applied sound field, surface tension at the bubble wall, viscous resistance in the surrounding fluid, and then the pressure of the gas inside the bubble. And it's the combination of all of these factors that determine how the bubble actually responds. So if the bubble has been able to nucleate and it's then exposed to the ultrasound field, what will happen is that it will continually expand and contract in response to the changing pressure from the ultrasound. Depending on the relative magnitude of all those different competing forces will determine on how the bubble actually responds. Now it's important to note the equation on the previous slide is only an approximation and it strictly applies to relatively small amplitudes of oscillation because we're not considering the compressibility of the surrounding liquid or any thermal effects, so we're ignoring any heat transfer from the bubble. If you start to drive the bubble at larger amplitudes, those do become important and you need to use a modified equation for this. But for now, if we just think about more qualitatively what the bubble is going to do, if we are driving it fairly gently at low amplitudes, then it will tend to just oscillate periodically. These expansions and contractions will continue as long as the ultrasound is being applied. If we drive it more violently, however, it may expand and collapse quite violently and not actually start to do that again for several periods, so it can oscillate non-periodically. Gas may start to diffuse out of the bubble, or indeed you may get vapor condensation, so the bubble can shrink. It can actually also grow, so there's a process known as rectified diffusion, whereby there's a net flux of gas into the bubble as it's oscillating, so its resting radius will expand. And if the surface becomes unstable, if the bubble is being driven very, very hard, it can collapse and fragment into lots of smaller bubbles. Now there are lots of different ways of classifying cavitation. One of the earliest definitions was so-called stable versus transient. This then brings us into another minefield of definitions, because stability means different things to different people. And in particular, it may refer to periodicity. So in the more mathematical definition of stability is that an oscillation continues showing a constant periodicity. It may refer to the fact as to whether the bubble is hanging around or not, whether it is persisting, or it may be the consistency of some secondary effect, for example, the acoustic emissions from the bubble. So stable is another term to be used with caution. A slightly more mathematically rigorous way of classifying cavitation refers to the rate of the bubble collapse. So this can be related directly back to the equation of motion of the bubble. And particularly the competition that exists between the pressure of gas inside the bubble and the inertia of the surrounding liquid. So if we go back to our Rayleigh-Placid equation and we rearrange it slightly, the pink box here is showing us the so-called pressure term. So this is the balance of the external and the internal pressures in the bubble. And competing against that is the inertia. So the surrounding liquid that's being forced out of the way as the bubble is expanding and rushing in as the bubble is contracting. And it's the competition of those that determine the acceleration of the bubble wall. So the definition that was given by Flynn back in the 1970s was to define cavitation in terms of this competition. So if the inertial function, so-called, reaches a magnitude that is larger than that of the pressure function as the bubble is collapsing, then the bubble is said to be undergoing inertial cavitation, i.e. its collapse is controlled by the inertia of the surrounding fluid it's collapsing very, very rapidly, and it's quite a violent process. In fact, the process can be so violent that the compression of the gas inside the bubble is sufficient for light to be emitted, for shock waves to be produced, and often it also results in the bubble fragmenting. So this is so-called inertial cavitation. If the pressure function, on the other hand, is dominant, then we get these much more gentle oscillations, so-called non-inertial cavitation. I will note now that many people also refer to that as stable cavitation, but as noted a couple of slides back, stable should be used with caution. Okay, so how do we turn that into something that can be used to compare between experiments? Well, it's quite difficult in an experiment to measure the inertia and the pressure function. That works very, very nicely with the model. What we can derive, though, are some things that we can measure experimentally. Particularly, the pressure function and the inertia function can be replaced by the expansion ratio. So the bigger the bubble gets, the more likely it is that it will collapse violently, i.e. that we'll get inertial cavitation. And so we can define a threshold in terms of the expansion ratio, the maximum radius to the initial radius. If that exceeds a certain value, then we will get inertial cavitation. Similarly, we may be able to measure the interior temperature by spectroscopy, and if that exceeds a certain temperature, that tells us the bubble is compressed beyond a certain rate, and we're getting inertial cavitation. Or if we have access to a high-speed camera, or we can infer it from acoustic emissions, we can define the collapse in terms of the bubble wall velocity. And so if that goes supersonic, so if the velocity exceeds the speed of sound in the surrounding liquid, then we have a very, very violent collapse. So this is very useful if we want to predict how a bubble is going to behave, and we know the initial bubble size, the characteristics of the surrounding field. So this gives us a rule of thumb to predict different types of bubble behavior. As I briefly mentioned, transient and inertial were often used synonymously, but we should also note that inertial cavitation can be stable. So I'd strongly recommend inertial and non-inertial as more useful definitions. One brief thing I should mention is how this relates to the types of thresholds that are used in assessing ultrasound safety. So many of you will probably have heard of the mechanical index. That is calculated in a very, very similar way in determining the bubble size and pressure at which you are likely to get inertial cavitation. So the mechanical index gives you the cutoff, the minimum at which you are likely to get inertial cavitation, depending on whether you know the bubble size or the threshold. Very important to note, though, that is a very conservative simplification of a very, very complex process, which is entirely appropriate for defining a safety index, but it shouldn't be used out of context. The mechanical index refers only to a single cycle of a 1 micron bubble in a pure liquid, and it shouldn't really be extrapolated as a measure for use in therapeutic ultrasound. The other point is that so far we've only been talking about single bubbles, whereas in practice we are normally talking about a cloud of bubbles, either produced as a result of bubbles forming from nucleation sites pre-existing in the medium, or where we've deliberately injected nuclei. And so as a result, because we will have a range of different bubble sizes, and we will also have a distribution of pressure depending on where we are in the medium, there will also be a distribution of thresholds, and not every bubble will do the same thing at the same time. So it's more practical to consider cavitation events in terms of the probability of their occurring. And it's fairly intuitive, but the higher the peak negative pressure that we're applying, the lower the frequency and the longer the exposure time, the more likely it is that we will both nucleate bubbles and that they will collapse inertially. Now, why do we care about bubbles in therapeutic ultrasound at all? Well, these dynamic processes, the oscillations of the microbubbles, can have a very significant effect on tissue over a significant range of both time and length scales. And we need to be aware of this because it can be harnessed to deliver therapy and actually enhance a treatment. And it can also cause quite significant damage if it's not controlled or if it's the wrong place. So we need to understand when and where cavitation is going to be occurring in order to control the process and derive the maximum benefit for therapy. So if we start at the sort of smallest length scale, the motion of a bubble in a liquid near a cell is known to create poration of the cell membrane. So it can actually temporarily permeabilize the cell, enabling uptake of drugs. Now, this is a slice through some brain tissue showing where drug has been able to pass out of the blood vessels as a result of the permeabilization of the blood vessel wall. And here is an absolutely beautiful real-time confocal video taken by Alfred Yu's group in Hong Kong, looking at the effect of a single bubble exposed to ultrasound at the wall of a cell. And what you see is that pore opening up when the ultrasound is applied and then resealing over time. So we can both permeabilize individual cell membranes and we can permeabilize cellular membranes, so the endothelium lining a blood vessel. Both of these effects can be very useful for enhancing drug uptake. Another very key effect produced by bubbles is their ability to set the surrounding liquid into motion, so-called streaming. So because the bubble is oscillating in a very nonlinear fashion, momentum is imparted to the surrounding liquid, and it is, because it's nonlinear, that process is asymmetric, and so you get a steady flow being produced around the oscillating bubble. That's what we're seeing here. There is a bubble located here. We have some fluorescent particles in the surrounding liquid, and you can see the flow that the bubble is producing. And that flow can be quite rapid. There can be very, very high velocities local to the nearby tissue, and the shear stress produced by the motion of that fluid can both affect the permeability of that membrane and also the convection of drugs in the surrounding fluid. Now, as we increase the intensity of the ultrasound field, so as the peak negative pressure increases, we start to get more violent effects. So here are some videos in a block of agar taken by my colleagues in Bubble in Oxford, showing ultrasound being applied to a tube containing a dye in the absence of bubbles, where very little happens. But if there are bubbles present, you see you get this very, very large cavitation cloud being formed and convection of the drug into the surrounding gel. And this is thought to be the reason why we see this enhanced extravasation of drugs from the bloodstream into the surrounding tissue when we expose to ultrasound and bubbles. A further important effect of bubbles is their ability to dissipate heat. I mentioned we were neglecting that in the Rayleigh-Placid equation, but experimentally it is something that's very, very important. As the bubble's oscillating, we have heat dissipation due to viscous friction. The fact that the bubble is itself re-radiating ultrasound and doing so at higher frequencies that are readily absorbed. And also there will be a little bit of thermal conduction due to the gas being compressed and heating up. And all of these contribute to a quite substantial temperature rise in the liquid immediately surrounding the bubbles. So what you're seeing here is the temperature rise measured in the liquid close to the bubbles as the amplitude is increased. At low pressure amplitudes, we see a linear heating curve, which is what we'd expect. But at this point, which is the cavitation threshold, suddenly the temperature rise jumps quite dramatically. And that's due to this temperature thermal enhancement effect of the presence of bubbles. And that's extremely useful in therapeutic ultrasound because it means we can accelerate the rate of heating in tissue and hence reduce the duration of the treatment. And then lastly, we also have to consider the chemistry that's going on inside an oscillating bubble. So as we mentioned, as the bubble is compressed, the gas inside is being heated up to a very, very large degree, and obviously the pressure is simultaneously increasing. And that rise in temperature and pressure can be enough to produce some very interesting chemical effects. And as we see in the video here, it can actually be enough to produce light, so-called sonoluminescence. Now, these very, very high temperatures and pressures are confined to the core of the bubble, so we're not getting heating of the surrounding liquid to 1000 degrees, but it is able to produce some highly reactive chemical species, reactive oxygen species, that will affect the immediately surrounding tissue, and can also be used as a way of activating certain types of drug. So for local drug activation, we can exploit this technique in so-called sonodynamic therapy. As we increase the violence of the bubble behavior, another phenomenon that's quite important is so-called microjetting. So far we've implicitly assumed that our bubbles are oscillating spherically. In reality, if the bubble is near any surface, or if it's near another bubble, there will be asymmetries in the acceleration of the liquid around the bubble that in turn stops the bubble from being perfectly spherical. As you can see here, we get this little dimpling in the surface of the bubble as it's oscillating. That's because we've got a surface somewhere over here. And if the bubble starts to collapse and it is in an asymmetric configuration, then it will sort of turn in on itself. It forms a donut shape, and the acceleration of the fluid through the bubble can be very, very high, and this produces these high velocity microjets. So the liquid coming through the bubble at very, very high speed, and the jet comes out the other side. So this very beautiful picture taken by Professor Larry Crum some years ago now is showing that process happening, this high-speed liquid jet, in this case being directed towards the nearby surface. And this jetting effect can be very, very significant. These velocities are very, very high. They're more than sufficient to erode tissue. This is an effect that's exploited in tissue ablation. So here you're looking at a blood clot that over 30 seconds has been quite significantly eroded as a result of this microjetting behavior. It's one of the contributory mechanisms for histotripsy, which there's a whole talk by Brian Fuchs on if you were interested, and also in lithotripsy, so in the destruction of solid stones or calculi in kidneys. Now, as we say, one of the things we want to be able to do is to harness the power of cavitation in therapeutic ultrasound. So it's not only important to be able to understand and predict how bubbles behave, we also want to be able to measure that, preferably in situ, so that we can monitor a treatment and make sure the cavitation is occurring in the right place and is of an appropriate intensity. There are different ways we can do this. Ideally, we would use a very high-speed camera to watch the bubbles as they oscillate. This is absolutely fine in the lab. It's sadly not quite so practical in tissue. We can use chemical detection. We can, for example, detect these very reactive species that are produced by the bubbles, but again, that's quite tricky deep in tissue. So the most practical way for treatment monitoring is to use the acoustic emissions that are produced by bubbles. And what we're doing with these typically is we're listening for the secondary sound fields that are produced by a bubble as it oscillates. Now, as the ultrasound comes in, pressure is changing, the bubble is expanding and contracting, and as it does that, it's acting as a secondary source of sound, and it's producing sound field where the pressure is dependent on how fast the bubble wall is moving, its acceleration of velocity, and then the properties of the surrounding fluid, and of course its size. And the sound field spreads out as a spherical wave, so it decays as 1/r. Now, one of the great things about bubbles is because they are so compressible, because they're full of gas, they actually produce incredibly strong acoustic emissions or scattering. So compared to a rigid sphere of the same diameter, they can produce a sound field that's several thousand times stronger or even more. They're incredibly efficient scatterers. And also because these oscillations that they are undergoing are nonlinear, the acoustic fields that they produce contain a range of different frequencies. So if we drive a bubble at one frequency, the secondary sound field they produce will actually contain a range of frequencies, multiples of that driving frequency, and sometimes fractions as well. So what we're looking at here is the radius time curve of a bubble. See, it's expanding and contracting. And as you can see, although we're driving the bubble sinusoidally, it's not responding sinusoidally. And if we look at the frequency content of the resulting sound field, we see it contains the driving frequency, but also multiples or harmonics. It's that harmonic content that allows us to distinguish a bubble signal from the surrounding tissue. And that's an effect that's already exploited in ultrasound imaging. Bubbles are widely used as contrast agents. They're injected into the bloodstream, and they're nonlinear echoes can be detected. And so that's one thing we can use for treatment monitoring as well. We can, just as in ultrasound imaging, use pulse echo techniques. We send in a short pulse of ultrasound, and the backscatter from the bubbles tells us where they are and what they're doing. This is so-called active imaging. But we don't actually need that initial pulse, because in therapeutic ultrasound, the bubbles are already oscillating. They are already producing a sound field, and we can just listen passively for that. Now we can do that with a single transducer, which will give us a rough indication of where cavitation is happening, but we can also do it with an array of transducers, so-called passive acoustic mapping, where because of the different time it takes for the bubble signals to arrive at the different transducers, we can actually work out where bubbles are as well as how much they're oscillating. And that's very, very useful, because we can overlay the map of cavitation activity on our anatomical map from another imaging technique, so that we can work out exactly where cavitation is happening in real time during a treatment. So just to give you an example of this, this is an ultrasound B-mode image of a piece of tissue, and we're able to overlay our cavitation map on top of that, and we can check that our most intense cavitation activity is occurring within our focal region that's been lined up with our treatment zone. So we can make sure in real time the cavitation is occurring where it needs to be. And as I mentioned, that harmonic content can also give us some useful information, because it tends to change as we increase the pressure with which we're driving the bubbles. So the harder we drive the bubbles, the more nonlinear are their oscillations, and so the harmonic content in the bubble signal will change. So here, if we drive the bubbles gently, we see these sort of single harmonics being produced. We're driving it hard enough that we're also getting some fractional harmonics as well. But as we increase the drive pressure, we start to see this region here, this sort of broadband noise. We're getting emissions over all these frequencies. This component starts to increase as we drive the bubbles harder. And roughly speaking, that broadband component can be used as an indication of inertial bubble behavior. I need to sound another note of caution here though. Cavitation signals should be interpreted with extreme care. Nonlinear propagation can also produce harmonics as well as oscillating bubbles. You can usually distinguish it from the amplitude, but yeah, be aware there are lots of nonlinear processes occurring, particularly in therapeutic ultrasound. Frequency content will also be affected by non-spherical bubble oscillations and bubble-bubble interactions. So you can get a very, very nonlinear behavior at low pressures if you have a large enough bubble cloud. And also the range of bubble sizes is continuously changing. Bubbles coalesce, bubbles collapse, they fragment, and all of that can produce a wide range of frequencies in the signal that can look just like broadband noise. So it's not a simple correlation between broadband noise and inertial cavitation, it's just a useful rule of thumb. And of course, depending on the electronics that you're using for detection, the bandwidth of the transducer, and all of the other restrictions in your electronic setup, and the resolution with which you're able to interrogate the signal will also affect what you're able to measure. So I'd like to end with the 3 commandments of cavitation physics, which were given by Professor Robert Apfel, who was one of the founders of this field, which is know thy liquid, know thy sound field, and know where something happens. Thank you very much.